Hey there. In this video, I want to talk to you about spiky neural networks and what kind of improvements they can bring over traditional neural networks. But first, let's start by asking us the question, what exactly is a neural network? What defines it? Well, there's no standard definition, if you take it fast, but I think we can classify any sort of graph with nodes and transitions that has an input and an output and some sort of transition functions between the nodes as a neural network. Going into computer science, we can see that things are a little bit different. Typically in traditional neural networks, nodes or neurons as we will call them from now on, are organized in layers. We have an input and an output layer and any number of so-called hidden layers in between. All neurons of a layer are connected to all neurons of the next layer, and this way we get a feed-forward system that can be described as a mathematical function doing some sort of operation on the input. This operation on the input is of course a series of operations that the individual nodes will perform on the inputs that they get from the previous layer. So we have to use what's called an activation functions, which will determine the output of neuron. So let's start by taking the weighted sum of all the inputs. With this, we of course want to normalize in order to sort of contain the range. First thing we can do is use what's called a perceptron. Perceptron simply says if the weighted sum of all the inputs is bigger than our threshold, then we output 1. Otherwise, we output a 0. So we get this sort of function to determine whether it's an input or an output. Now, of course, this is not always optimal. We might not want this steep sort of curve, but make it a little bit more smooth. This is where the sigmoid neuron, another standard way to code neurons, is coming into play, as it does exactly what we needed to do using an exponential function. But let's talk about pros and cons first. First pro is, of course, it's easy to use. I think we can agree on that it's not that hard to implement in code. Another plus point is, of course, that it can approximate any mathematical function to the wanted degree. As we said earlier, that it's in principle only a huge mathematical function that we have here. Furthermore, it can be used without much knowledge of the underlying problem, as you might have heard in the media. Many people apply these sorts of techniques to almost any problem, and it works if you have enough data. Which brings us to the cons. The first point on this list would directly tie into the last one from the previous, and that it's a black box that people don't need to understand the problem to apply it. And sometimes, if you don't have enough data, then you will wonder, hey, why isn't it working? Next up is the computationally expensive nature of this type of neural network. As the more complex the task gets, the bigger the network gets, which ties into my next point that I think it's overused, as you can use it for almost any task. If you scale the network accordingly, people disregard other methods of machine learning. And if you want to stay close to biology, I think this is quite far. It's very abstract to how neural networks work in biology. This now ties into the next segment I want to go into before we go to the spiky neural networks, which is if we want to stay close to nature in our engineering, what do neurons actually look like? I think we need to understand that to use it for our advantage. Let's look at the brain here. Assume this is your brain or someone's brain. And let's zoom in a little bit. Of course, this is not to scale, but how does it, schematically at least, look like to zoom into a couple of neurons in your brain? First off, every neuron has a nucleus, which is the switch, so to say, that decides whether the given inputs should result in output. Then we have dendrites, which are the spiky things coming off of the nucleus. These are, so to say, the inputs. They connect to the axons we're going to come to later. of other neurons. Axons are then the output, which result in synapses to other neurons. Synapses are the exact coupling points to the other neuron. So how does a neuron decide whether it should fire or not? Well, picture a membrane where ions in the neuron's nucleus can pass through depending on the circumstances. So these ions then create a potential, right? If there's more, in most cases, calcium or potassium ions on the outside of the membrane, then there's a potential. And depending on the input, if there's an input spike, these potentials shift. So ions are allowed to flow through the membrane and there's a different potential. If this potential then reaches a threshold, then the neuron itself spikes based on the input that I got. I'm gonna demonstrate this here really quick, where the threshold in most cases can only be met when multiple inputs overlap each other, which is one of the nice things about these spiking models, is that they are time dependent. So as you can see here, if we have an input spike at some point in time, which doesn't conclude in the threshold being reached, but at some later point in time another input spike, so the same input might spike again, then the potential is enough to cross the threshold and the neuron in turn will then fire a spike. Knowing this now, the question becomes, how can we model this for us to use as computer scientists? Of course, we can't go into each and every way to model this, but one very common way is the leaky integrated fire model, which we'll show you right here. We simplify the previous schematic to having an axon, a synapse, a soma, or in this case just a switch, and we build a electronic circuit that can replicate this. Now, you don't need to know exactly the details of this model to understand it, but first thing you need to know is the switch on the left side of the synapse representation always closes when there's a spike, so this is something that you have to keep in mind. And once this closes, the circuit obviously closes, we get a current flowing, and with the equations that you can see on the screen, we can describe the behavior of the circuit once the switch closes, which is very nice because these are differential equations. We can solve them quite efficiently, and we can then calculate the potential that should be measurable in the point theta. If this potential then crosses a certain threshold, then we say, okay, fire another output spike to the next neuron in line, or the next neurons. One thing to keep in mind though is that this has to be done manually in this model. Knowing now how to construct a singular neuron, let's talk about how to construct the entire network of neurons. First off, we need some sort of input, right? So as an input we usually set some sort of spike generator that we directly connect to a couple of neurons, which ones these are every time dependent on the task or the architecture we're going for. But we connect spike sources to neurons. Next up, we have our neurons floating around and we connect them. So we can connect each neuron to each other neuron, or we can connect them selectively. This of course is subject to optimization in order to get the behavior that we want the network to have. And lastly, of course, we pump information into the network via the spike generators. We need to get some information out, which we have different options for. We can read out the potential that some neurons are displaying at different points in time, or we can read out their spike rates and get information from that. With all that said, we now have obviously to train a network, which we haven't talked about neither for the traditional nor the spiking networks. How do we train a neural network? One way is for the traditional neural network, backpropagation, which I'm going to explain real quick. Is, as I said, the traditional network can be seen as just a massive mathematical function. And of this function, we can build the gradient. Not only the gradient of the function, but the gradient of the error functions, as we usually know what the output should be of our network when we train it. So we have this error function, which we can get the gradient of with regards to the weights and biases that we set to be the parameters of our network. Doing this in an iterative way will make sure that we end up at a local minimum in the end of our training data. Or maybe not the local minimum, but we'll converge to a local minimum with enough training data. Now, the important thing is, as I mentioned, this cannot be done with the spiking neural network, as spikes, as it is their nature, are not differentiable, and therefore we cannot build this gradient. So, what do we do? Well, there's a technique called evolutionary algorithms, specifically genetic algorithms, which I'm going to go into, where we encode the parameters of our traditional neural network or spiking neural network as a DNA string, where we generate population of these in a random fashion, and then we evaluate their performance on our training data, see how good they are. Of course, we need then a fitness function, what it's called, to evaluate this. Then we select the top performers and we breed them, so to say. As in biology, we would just cross over their genetic information, the specific implementation of which varies from case to case. But after that, we introduce a small possibility for random mutation in order to avoid getting stuck with some strain of breedings, and we're done. Another way to tackle the problem of learning specifically in the spiking neural networks is the so-called spike time dependent plasticity. The basic idea can be described as rewarding the behavior that we want, meaning that if we have a neuron and the neuron first receives an input and then fires an output in close temporal proximity, we will reward that by strengthening the impact that this input has on the neuron's decision. The other way around, if we detect an output of the neuron and afterwards it gets an input, this input obviously doesn't have much to do with the output and will lessen the impact. So, if we have multiple inputs to neurons in a network, we'll see that over time some inputs lose almost all their impact or might completely die, and we will sort of get a simplification of the network, where only those connections remain that actually contribute to the wanted behavior. Next up is what we would call modified backpropagation. We've talked about how backpropagation is sort of complicated with the spiking neural networks, because spikes by their nature are not differentiable. If you can imagine sort of this kind of spike, then you can easily see that we can't form a derivative at the top or the bottom. But if we sort of smoothen this spike out, then we can indeed use backpropagation. We'll have a source with the exact workings of this in the credits screen. But for now, let's wrap this up by coming back to our pro and con listing, which we did for the traditional neural networks, but this time for spiking neural networks. One of the points that we said was not that good in traditional neural networks was, of course, that they're not very bio-inspired, which, depending on the model, the spiking neural network models are very, very close to nature. Next up, we can safely say that they are more powerful, as they not only allow real-time evaluation of tasks better than traditional networks, but also can be more of a real network, as neurons can be connected to every other neuron and are not organized in layers as they are in traditional neural networks. One other plus is that they are usually much smaller for the same task, meaning that you can view what's going on, you can observe what the network does better than in traditional networks. They're also better for real-time applications, as you might be able to imagine, because they're continuously receiving spikes or producing spikes. And lastly, an interesting observation that can be made is that at least in bigger networks, there have been cases of momentum, where an input might produce a series of spikes in the network that lead to the network, even without an input, continuing a cyclic behavior of sorts. But of course there are also con points, one of which is that they are rather complex to implement. As you might imagine, the traditional networks are much simpler to implement. They are difficult to train. We can't just use backpropagation usually, as with traditional neural networks. And in some cases it is advised to use special hardware that implements these electronic circuits in hardware to make them faster. And the last point is that the many different models often are quite subtly different, which makes it hard to decide which one to use. Alright, this I think wraps then up our video on the spiking neural networks and how they are a little bit different from the traditional approach to neural networks that we can find being used right now. Of course, this was very brief and very quick, but I hope we could spike your interest, and maybe you'll have the time to read up on some of the sources we posted, some of the research that is going on. And with that, thanks for watching.